showing the introns and exons. So here's exon 1, and then there's an intron, and here's exon 2, and then there's an intron, and here's exon 3, and then there's an intron, and there's exon 4. You will recall, because we've talked about it a lot, that for our RT-PCR experiment, the forward primer was in the middle of exon 1, and the reverse primer was in the middle of exon 2. And if we amplified a product from RNA, then we would get a 150 base pair product because it would include part of exon 2 and part of exon 1, right? Everybody remember that? Yeah. You, in fact, did get a 150 base pair PCR product on your gel, which we said, oh, that's your TTR-PCR product, proving that, in fact, TTR is expressed in adult liver because you got a band on a gel at the right size. But in real life, you would want to sequence that in order to prove to people that what you amplified really was TTR, and therefore you could say with certainty that TTR was expressed in adult mouse liver. So in fact, we did that. We sequenced it, and it was run. You sequenced it several days ago. It ran on the sequencer, and now you have your data. So let's take a look at the actual sequence of TTR. It's down here, further down on page 126. I apologize for it being so faint, but on NCBI, this is the way it looks now. It used to be in the old days when it was a little cruder and not quite so fancy, you could actually read it on a piece of paper. Anyway, exon 1 is here in the red and the blue. That's exon 1. Then this is the intron. It's keyed over here, so exon 1, intron 1. This is exon 2. Then it's intron 2. And when it says intron 2, 3, that just means it's the intron between exon 2 and exon 3. It's a weird designation. Not my fault. I didn't do that. Okay. Now, where are our primers? Our primers are located right in here. There's a forward primer here, right in this area, and the reverse primer is down here in exon 2. And what we would amplify would be this sequence of exon 1, and then the sequence of exon 2 until we get to the primer. It's a pretty short sequence, only 150 base pairs. Now, we can actually find the beginning of the forward primer. If you go on page 111, I'm not going to do that because I don't want to lose my place here, but on page 111 is the sequence of the forward and reverse primer. The sequence of the forward primer starts ACA-CA, I'm going to put my cursor right there. See that A right there? Y'all see that? ACA, GA, TCC, ACA, down to ACAG at the end of that primer. ACAG at the end of the primer is right here, ACAG. Our forward primer ends with that G right there. Okay. So we did PCR with the forward and reverse. I'm not going to look for the reverse down there, but it's in the middle of the second exon. The forward primer we also use for sequencing. So primer to sequence through our PCR product. Now the way sequencing works is the very first nucleotides that come off the sequence you can't actually read because it's too messy, the fragments are too small, the matrix doesn't resolve it well. So you're not going to read right off the end of the sequence. So the end of the primer is G. We're not going to pick up the sequence at this first G. It just doesn't happen. It's going to happen about 10 nucleotides down. Okay? Because the first few fragments that you make are too small for the matrix to resolve. Okay. So we're going to start the sequence a little further down, but we're still going to be in exon 1. So I want you to open your sequence in FinchTV and let me see if I can show you how to do that. Lost my FinchTV window. should open and look like this, except it won't be blue. Blue for me because I highlighted something, so don't worry about it. Everybody have their sequence open? Okay, for some reason I couldn't open your sequences, so this isn't one of yours, this is one from last year that I opened, but it doesn't matter, they're all PTR gene sequence. But your chromatogram should look something like this. Now you can stretch things out by doing this, back and forth, so you want to stretch it out so you can read the sequence a little better. Yeah, if you stretch it, it's easier to read. The peaks tell you the sequence. So if you look at this, T is a red peak, a G is a black peak, an A is a green peak, and a C is a blue peak. So that's just the 4 colors of the 4 dideoxynucleotides. And because the instrument knows what color A is, what color C is, what color G is, and what color C is, it can read the sequence. And so as those bands pass by the laser and the detector, it's able to read each band and call the sequence. And so it did that for each of your sequences simultaneously. They were run at the same time. And it was able to call each nucleotide for you. Now, my understanding is that for whatever reason, the sequencer, what did Ricardo say? Do you know?
He was having a little bit of trouble with just like background, but I think he may have got it.
So,
I wasn't around.
so anyway, I wasn't able to open your sequences, but they may or may not look as pretty as this. They look nice? They look as good as this? Okay, good. That means Ricardo was able to fix the problem. That's good. Okay, so if you can read this sequence, then we can proceed. So if you look, it's before I highlighted in blue where it starts getting good. Before this, it's a mess. I would not try to read this. The instrument tries to call the bases, and maybe it called some of them right, but we're not going to worry about that. We're going to pick up here where this T looks pretty good to me, and then that C, and then TT, and then C, and then C. It's calling this 2 C's because it's really broad, and at the beginning things are a little difficult because again the fragments are small. It gets better as you can see going to the right here. Anyway, it's making the calls going down. So I took a chance and I highlighted starting at this T, and I highlighted all the way to the end. So what you want to do is to highlight starting wherever your sequence looks good, and then just drag across and it'll highlight the entire sequence from that point on. You have to click on the nucleotide and then drag going to the right to highlight the sequence. If you have trouble, raise your hand and Kalani will come over. Okay. Oh, you're good? Is everybody able to highlight their sequence? Okay. Once you've highlighted your sequence, go up here and click on copy, and you'll copy your sequence to the clipboard. Everybody copy their sequence to the clipboard? You guys are good. There's what was your question? No? Okay. Okay. All right, now what I want you to do, now that you've copied your sequence to the clipboard, is to go to NCBI, open a new window, and go to NCBI, and get to the NCBI homepage. Everybody on the NCBI homepage? How you doing? Great. Never goes this smoothly. Everybody's really good. Wow. Wow. You guys are amazing. Sorry, what about the Wi-Fi? Oh, you got disconnected? Yeah. Get disconnected regularly. Alright, well, good reason for going slow. Alright, click on BLAST, it's over here on the side. Everybody see BLAST? Click on BLAST, and it takes us to the BLAST page. And then what we're gonna do this time is we're gonna click on nucleotide BLAST because we're gonna use a nucleotide sequence to query the nucleotide database. So click on nucleotide BLAST and you'll get to this window. Okay, we all good? Amazing. Then click on the, well, normally this takes hours because everybody's having trouble. Lonnie's up there going, yeah, that's nice. Alright, in this box, click on the box and then paste in your sequence. Copy to the clipboard. Now you've copied in the part of the TTR sequence that you could read that was good. And now just forget all this other stuff and go down to here and just click BLAST. And what it's going to do is it's going to compare your sequence to every known sequence in the nucleotide database. Boy, was that fast. Yeah. Yep, and the first hit you get is to musculus, transthyretin, and on the sequence I had, it is 100% identical match. This column here is identity, so even though we started really early in the sequence where things were still a little dicey, the instrument made all the correct calls because we have a perfect 100% match to the TTR gene from musculus. Pretty cool. So that shows then that the product you got that was 150 base pairs that we thought was TTR because we used TTR primers and got the right size product, it really was TTR. So now you can say with confidence from that experiment that TTR definitely expressed in adult mouse liver tissue, right? And then once you know that, then you might go on to do the quantitative PCR experiment that we've already done. You already know the results of. You know that TTR is expressed at pretty high levels in adult mouse liver tissue, and you know that from last time. Yes, sir.
Are all of those other hits that it's also 100% matched with just other things that people have posted that are parts of the TTR gene?
So remember, this is everything, right, in the database. So the first hit is to transthyretin mouse. The second hit is to somebody else entered a sequence, clone of TTR. These are all clones. Musculus, TTR variant X1, that's that TTR mRNA variant that we mentioned. Here's TTR again. These are all 100%. Keep going down. Here's one labeled pre-albumin. That was what transthyretin used to be called because it ran before albumin on the shell, so they called it pre-albumin. That was before they knew what it did. You keep scrolling down. These are all different mRNAs that have been entered into the database. So anybody that sequenced transthyretin and entered it into the database, you're getting hits to. Eventually, you get to muscaroli. It's a different mouse species. It's hitting mouse caroli at 99.05%. So there was a nucleotide difference or two there between musculus and this other species. Then there's I'm not pronouncing it, but anyway, you can see we're starting to get less than 100% matches because these other mammalian species that we're getting hits to, different species, a little bit different sequence.
I just wanted to see what
So, if you didn't get 100% match, that's because you probably had a sequencing error. The instrument made a wrong call somewhere. And if you find that nucleotide, that's the miscall, then you can go back to your trace and look and see what the situation is. Sometimes you go back to the trace and you can see why the computer made the mistake. If we scroll down, Scroll down, scroll down, scroll down, oops, scroll down. Okay, so if you click on alignments up here, it'll show the alignment of your sequence and the first hit, which was the musculus transthyretin mRNA. Your sequence is the query. So we have, in mine, I have nucleotide 1 to 107. And everywhere you see a solid line, that's because it matches, right? I have no mismatches in mine. Where's your mismatch? So somewhere over here? In here? Oh, down here. Oh, over here somewhere? Okay, so if you go to your trace, you could look there to see maybe why there's a problem. That might be in a region where the dideoxynucleotides came out. I'll show that in a second. Okay, everybody see what we did? How many people got 100% match? How many people got 98% match or above? Okay, so there are some places where it was a little rough and the instrument might have made a miscall, or it wasn't able to make the call and it puts an N or some other letter, and if it did that, then it's going to call that a mismatch. And that's just the instrument not being able to make the call. Yes?
What we did have a lot of was, dialogues
Yeah.
around that 78
Yeah.
region, so a lot of people probably have.
Yeah. So I'm going to show that next. So if you go back to your trace, go back to the trace here. If you look at around nucleotide 80 to 90 in this region here, see how 80 to 90, there's these really high peaks and there's this blob here. That's where the dideoxynucleotides come out that are not attached. Remember, we put our sequence reaction through a zymo column to get rid of the unincorporated dideoxynucleotides, but you can't get rid of them all, and so you always see this rough area here at about 80 to 90. And if you've got a nucleotide mismatch or a place where the instrument couldn't make the call and it put N, then it would probably be most likely in this region here.
There were also some K's and R's in there.
Yeah. So if it can't decide if it's an A or a B, then it puts R. If it can't decide if it's a C or a T, it puts Y, I believe. I think K is when it can't decide between A and C. Anyway, the different letters are when it can't make a decision, can't make the call. And so sometimes if you eyeball it, you can make the call yourself. If you can, then if this was a gene sequence that you wanted to publish, you've got the sequence going the other way, and you'll be able to resolve it with the other strand. And we'll take a look at that when we do gap DH later this afternoon, because with gap DH we did forward and reverse. Here we only did forward. Why did we only do forward? We don't care if we get a perfect sequence here, because all we were doing was using this to show, or to answer the question, is it transthyretin? We don't need a perfect sequence to do that. This is definitely transthyretin. And if you've got a nucleotide mismatch in that 80 to 90 region, doesn't matter because we've already got our answer. We know it's transthyretin. If we were going to publish the sequence, that would be a different story. But transthyretin sequence is already published, already known, no need for you to publish it, right? You were doing a gene study.
What happens if there is a mismatch between the forward and reverse?
Yeah, so if you have a mismatch between the forward and the reverse, if the mismatch is clearly because there was a little messy spot in your forward read and the reverse read gives it perfectly, then you're confident that the reverse read is the correct one. If it's in some other region where there's a discrepancy, then you're going to have to sequence again to try to resolve the problem. Because sometimes you get a problem when you run the sequence the first time, you run it again, you don't have the problem the second time. But if you're gonna publish the sequence of the gene, you definitely wanna be 100% certain you've got the right sequence. If you don't wanna be corrected later, that's embarrassing. Okay? It used to be, before sequencing got so good, that people put things into the databases all the time that had a few errors, and then over time they got fixed. People were contacted and said, oh, you know, your sequence is a little wrong here, and then they could go back in and fix it. But it's a slow process. That's why I say when you look up sequences, if you see something that's pre-2000, you know, you want to be a little skeptical maybe. After 2000, then things improved a lot. Okay? Yeah.
So the intensities, they vary wildly, even when
Yeah.
they
Yeah. So remember that each of these bands comes from a termination at a specific nucleotide. Remember, these are terminations with dideoxynucleotides. And remember how when we were doing this on the board over there, say we were in the G tube, we'd get terminations at all the G's, but only in some of the molecules, and that's why synthesis could continue. So we got to the first G, some would terminate there, but most would continue, right? You get to the second G, some would terminate there, and most would continue. The efficiency of termination at each position is going to be a little different. And that's why the peak heights are different, because if you have efficient termination, you'll get a higher peak. If you have less efficient termination at a particular spot, you'll get a lower peak. Good question. So that explains the peak height. The space between the peaks is just like the space between your bands on a gel. And so as you go further down your sequence, they're going to get closer together and harder to differentiate. So on these sequences, they're short because our PCR product was only 150 base pairs. If we go over to the right, the sequence goes and goes and goes, and then it just falls off. Well, why does it fall off? It's the end of the sequence, right? It was only 150 base pairs. So it'll just go, 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 and then fall off. Now, if we have a much longer one, like we do with the GAP-DH that we're going to do this afternoon, we're going to go so far down the sequence that things are going to get too close together, and then the instrument will not be able to make the calls anymore. Even though the sequence keeps going, even the instrument can't read it.
Is that 150 base pairs? It looks, even on ours, like less than that.
Okay, so we had 150 base pair product, right? The sequence primer is the forward primer. So you hybridize that primer. The primer, I think, was 22 or 3. And then you prime off the end of that. So you automatically lose 23 because of where the primer hybridizes. Then you start sequencing after that. Then you lose about another 10 because you can't read the first 10. So you lost 20 because of the primer, 10 first nucleotides, now you're down 30. So you're probably going to get 120 nucleotides in sequence at the most, right? And again, here, if we get 100 nucleotides a sequence, or even just 50 nucleotides a sequence, it's enough to see that it's TTR. We don't need the whole sequence. In fact, we only amplified really a small part of the gene.
Why in the horizontal axis, why do we have a continuous spectrum and not like just points in the individual things?
I'm not sure I understand the question. Say again?
I mean, we have individual base, right? It goes 20, 21, 22, 23.
Yep.
Shouldn't we have just a peak at every bin and not like a continuous spectrum going up and down? We have stuff in between the base.
Oh, it's just the fluorescence. So the instrument excites the band as it goes by, and then you get a signal from that. But the gel material, the thing is still running, and so it spreads the peak out a little bit because it's actually running as it goes past the. Yeah, I see your point. Yeah, right.
Can you explain more about the dideoxynucleotide in a couple observational? Is it always usually run like a
Yes. Yeah, it's always in that same region, and that's because when they're free, for whatever reason, they run bigger than when they're attached. I don't know the physical chemistry behind that. I've asked people at Applied Biosystems, and I get some sort of weird hand wavy answer. But the answer is that's where they come out, and it's always in the same place, and it causes the same problem. If you take your sequencing reaction and put it through a zymo column a second time, a new column, put it through a second time, so do a double purification, you can actually knock that down. And if you're having a real problem reading a particular region because of this, you can do that. You can put it through the zymo 2 times, and then you'll get rid of more of that, of those free nucleotides, the dideoxys, and then you'll be able to read the sequence better. If we didn't put it through the zymo, there would be this huge blob in that area, and there'd be about 30 nucleotides of sequence you wouldn't be able to read at all.
If the product is a less than 80 base pairs, it needs to
If your product is less than 80, you would get about the first, well, you'd get about, you'd lose the first 30, so you'd get about 50. I mean, once you get too short, then this kind of sequencing doesn't make sense. So you can't sequence oligos this way, for example. You know, if you've got something 20 or 30 long, you can't sequence it this way. How do you sequence it? You're stuck with that horrible Maxim Gilbert stuff. Huh? Yeah, maybe. Yeah, I've never done that, but yeah.
So the physical meaning of the x-axis, is that just a position along the gel?
What you can think of is that the small things at this end pass the detector first because they're running through, think of the capillary matrix as a gel, because it really is, and it's separating things based on size. So the short things run by first, and the longer things come by later, right? And the longer they are, the longer it takes. And so the sequencer runs typically for a couple of hours to get through your sequence. For something like TTR here, which is pretty short, you wouldn't have to run it as long.
So you said that the enzyme has holes for this section.
So our 150 base pair PCR product, let's do this one forward. So here's our TTR PCR product. It's 150 base pairs. When we sequence, this is 5', 3', 5', 3'. For sequencing, we denature the 2 strands apart. We denature the 2 strands apart, and then we used a forward primer, the PCR primer that was actually used on this side. We used the forward primer to do our sequencing. So here's our forward primer. And we used the forward primer as our sequencing primer. And so we're going to start the sequencing reaction here, right? So if there was a T here, we'd get an A here. And if there was a T here, we'd get an A there. If there was a G there, we'd get a C here. So we're going to start reading after the end of the primer. That's why you lose this sequence here. You're not going to get the first 20 nucleotides. Likewise, the first 10, the instrument can't really read because those fragments are too short for the matrix to resolve well. So you're going to pick up the sequence down here somewhere, and it'll sequence along down your 150 base pair molecule. And when it gets to the end, the polymerase is just going to fall off, and that's going to be it. So when you hit the end, that'll be the end of the sequence. And so what you see is nice peaks, nice peaks, nice peaks, and then nothing. Boom.
But we have something in the middle that is very anomalous.
Oh, those are the di-terminators, yeah. So, when we're sequencing, when you get up to about 70 or 80 base pairs, in that region, that size region is where the di-terminators come out. The 3 di-terminators that were not incorporated in the sequence and that we didn't get rid of when we did the purification column. Those di-terminators come out at about that size. It's really big. I don't know why they run. I mean, these are big molecules. And so they come out, you know, around that 80 to 90 base pair region and make that big blob that makes it hard to read the sequence in that region. Okay? Any other questions about that?